Hello everyone, welcome to my channel. This is Dr. Vijay. Today we will learn common source amplifier with current source load using potential division method at 180 nanometer. The designed amplifier must satisfy the design specification as gain equal to 10 dB and the power of 300 microwatt. Here VDD is 1.8 volt. So using simple power equation P equal to V into I, it is very easy to calculate current as 166.6 microampere. Therefore, to satisfy the power requirement, we are considering current as 160 microampere, such that it will not exceed the maximum power of 300 microwatt. In order to design common source amplifier with current source load, which is the combination of NMOS and PMOS. First, we need to identify the sizing of NMOS and PMOS using Cadence Virtuoso. Here, open the workspace and click I from keyboard for adding the required component such as NMOS, VDC and ground. Then after, connect all the terminals using wire. Here, voltage at drain terminal we are giving as 0.9 volt, which is half of the VDD, as we are using potential division method. Open the transistor property and modify the length by 3 times of 180 nanometer, which is 540 nanometer, to increase the output resistance resulting in higher gain, and keep width as variable W so that we can identify the optimum width of NMOS using dummy DC analysis. Here, gate terminal I kept as default so that we can find the threshold value of transistor using dummy DC analysis. Then after, go for DC analysis and select DC operating point. Click on design variables and give initial value as 2 micron and run the simulation. Once the simulation is done, click on result, then print, then click DC operating point. And here you select NM0 transistor. One window will pop up. There you identify VTH is showing as 321.92 millivolt. Now use this equation to calculate VGS, which is equal to sum of source voltage, threshold voltage and 10% of VDD, which will come around 502 millivolt. The additional 10% of VDD ensures that the gate voltage is sufficiently above the source voltage to maintain a stable operating point without driving the transistor into sub-threshold or triode regions. Now modify the gate voltage as 502 millivolt. After that, we will perform optimization of transistor width using DC analysis. Here, select component parameter as transistor NM0 and give the DC swap range from 2 to 50 micron. After that, go to output setting and select drain node to get current versus width curve. Once simulation is done, we need to identify the optimized width that satisfy 160 microampere. For that, use H from your keyboard and identify width at 160 microampere. You can observe that width as 11.27 microampere. Now open the property of transistor and change the value as 11.27 micrometer. This is the complete NMOS sizing at 180 nanometer for 160 microampere current. Similarly, we have to find the PMOS sizing using same procedure. Initially, change gate voltage to default, modify the source terminal voltage as 1.8 volt and drain terminal as zero point 0.9 volt for dummy DC analysis to identify the threshold voltage such that we can find the new gate voltage to satisfy the optimum width and the current. Open the property of PMOS and modify the length as 540 nanometer as we did in the previous NMOS sizing and keep width as variable W. Here, change the finger as 5 such that during simulation it will have more range of width. Now, perform dummy DC analysis, check design variables and use initial value as 4 micron meter, which is 2 times of NMOS. Select DC analysis and run simulation. Click on Result, DC operating point, and then select the transistor to check the threshold voltage of PMOS. Here it is showing around 459.10 millivolt. Here use this equation to calculate the new gate voltage, which will come around 1.161 volt. After that, again, we will do the same process to optimize PM0 transistor width using DC analysis. Here, select component parameter as transistor PM0 and give the DC swap range from 4 micron to 100 micron. After that, go to output setting and select source node to get current versus width curve. DC operating point and then select the transistor to check the threshold voltage of PMOS. Here it is showing around 4. Once simulation is done, we need to identify the optimized width that satisfy 160 microampere. For that, use H from keyboard and identify width at 160 microampere. It is showing around 14.43 micrometer. Now open the property of the transistor and change the value as 14.43 micrometer. This is the complete PMOS sizing at 180 nanometer for 160 microampere current. Once we have NMOS and PMOS sizing, then we will perform the AC analysis for the complete circuit which we have as common source amplifier with current source load, which is a combination of NMOS and PMOS. Here we have to assign all the physical parameter and the transistor sizing that we already obtained. Choose the analysis type as AC and the frequency ranging from 1 to 1 GHz. Then simply run it. Once simulation is done, go to result, then direct plot followed by main form. Here you have to select dB20 and select the output terminal from the circuit. Here 20 dB gain we can observe as 9.64 dB. If you want to calculate minus 3 dB gain, then press H and type 6.64 dB, which is 9.64 dB minus 3 dB equal to 6.64 dB at frequency of 1.894 MHz. Moreover, we can also calculate unity gain, that is 0 dB gain, and it has a frequency of 5.89 MHz. If you want, you can observe the gain in linear form also by clicking on the magnitude. It will come around 3.108 volt. Now we need to perform transient analysis. For that, go to analysis and choose trans and provide stop time as 10 millisecond because the frequency that we have selected at input is 1 kilohertz. Now select input and output terminal from the setting output and then run the simulation. Now click on split current strip to observe the waveform in better way. If you want to see the peak to peak voltage of input and output, then first click the input waveform, then click calculator and search peak to peak within the function panel and then click calculate. Here it is showing around 1.958 millivolt. Similarly, do for output waveform, it is showing as 6.196 millivolt. If you want to validate, then multiply the input magnitude with the gain magnitude and you will get around 6.096 millivolt. This is how signal will get amplified. I hope you have understood the concept and design part. Thank you everyone. We will again meet in the next video.